let's talk about shifters, multipliers, and dividers. Shifters come in two forms, either logical shift or arithmetic shift. So logical shifters shift values to the left or right, and they fill the empty spaces with zeros. So for example, here's a logical shift right by 2 bits. So we start with this number, and we shift off these bits to the right. So that bit shifts. That'd be a 1-bit right shift, but we also want to shift off the second bit. So we're shifting by 2 bits, and what shifts in on the left are zeros. And so we get 0, 0, these 2 zeros that got shifted in, these 2 bits got shifted off to the right, and we get 0, 0, 1, 1, 0. Logical left shift is similar, but we're shifting to the left by, in this case, the same number of bits. And so we shift off 1, 2 bits to the left, and we shift in zeros on the right because we're doing a logical left shift, logical left or right shift. And so we get 0, 0, 1, these 2 bits got shifted off, and we get 0, 2 zeros shifted in on the right. Okay, so left shift, we shift off bits on the left side, and for logical shifters, we shift in zeros into the empty spaces. Arithmetic shifters differ only in right shifts. So in right shifts, instead of shifting in just zeros, we're going to shift in whatever the most significant bit is. So in this case, the most significant bit is 1. So our arithmetic right shift by 2 bits, we'll still shift off our 2 bits off the right. Instead of shifting in zeros, we're going to shift in ones. So we're going to get 1, 1, 1, 1, 0. So now we shift in ones, or whatever the most significant bit is, not always ones, right? If the most significant bit were 0, we'd also shift in zeros. So in this case, the most significant bit is 1, we shift in ones. And in logical right shift, no matter what that, it doesn't look at the sign bit. It doesn't look at that most significant bit, it just shifts in zeros either way. Okay, for left shifts, well, left shifts don't differ from, these are the same. Logical and arithmetic left shifts are the same. We shift off our 2 bits off of the left, and we shift in zeros on the right. And so we get 0, 0, 1, 0, 0, and you can see these are the same. So logical and arithmetic left shift is the same, but right shift may differ. They differ in the method. In arithmetic right shift, we're going to shift in the sign bit. In logical right shift, we always shift in zeros. Okay, so we have to look at what that sign or that most significant bit is to know what we're going to shift in. Rotators are similar to shifters, but instead of just dropping the bits off the edge, we rotate them around. So this is a rotate right shift, ROR, rotate right. We're going to rotate right by 2 bits. As this bit, this 1 falls off and shifts to the right, it actually rotates and comes back around to the front. And so we get that 1 here, and then that 0 rotates around next. Instead of just falling off, it rotates around to the front. So we get 0, 1. They're no longer on the end. They've rotated around to the front. 0, 1, 1, 1, 0. And left shift is similar. Rotate left is similar. These are gonna, this 1 is gonna rotate around. Instead of just falling off the left, it rotates and then lands on the right. And then this 1 rotates and lands on the right. And so we get, right, they're no longer on the left here. They've rotated around to the right. We get 0, 0, 1, 1, 1. If we'd done another, instead of rotate right 2 bits, if we'd rotate right 3 bits, then we'd get this 0, not just falling off the left, but then rotating around and coming to the right. That would be rotate left by 3 bits. Then we get 0, 1, 1, 1, 0. Right? Fall off the left and land rotate around to the right. So let's talk about how we design these shifters. So, well, let's take an example of a 4-bit shifter. 4-bit, we'll start with a left shifter. Remember that arithmetic and logical left shift is the same, so it was called a left shifter, shift left. And let's start with a 4-bit number. The input is A3, A2, A1, A0, so a 4-bit input, and we'll have 4-bit output. Well, how much could we shift this by? Well, we could not shift it at all, so 0 bits. We could shift it by 1 bit, 2 bits, or 3 bits. Right? Okay. At that point, if we shift it by 4, now we get just 0, so that would be silly. Okay. Well, this looks like a good place for a multiplexer. So let's see what happens. So we have a select line. We want to make it have 4 options, so we need 2 bits. We'll put a shift amount signal, shift amount, SHAMT, signal to select how much we're shifting by. So if we shift by 0 bits, well, we feed AN, this 4-bit signal, and we just get A going to Y, and that's what we want, right? We want no shift of A. Okay. Well, what happens if we wanted to shift left by 1 bit? Well, let's see. So we have our input, A3, A2, A1, A0. This A3 would shift off, right? That would shift left, and then we get a 0 here. Okay, so we can take our A input, and we could even, write it something like this. And we want A2 to 0 and a 0 on that rightmost bit. Okay, what about if we shifted by 2 bits? Well, now both of these bits would shift off, and we'll get 2 zeros on the right. So if we were shifting by 2 bits, we'd want a 1 to 0 and 2 bits of 0 on the right. And what about our last option is 3 bits? Well, then all 3 of the most significant bits shift off to the left, and we get 3 zeros on the right. And so we'd get A sub 0, and now 3 bits of 0 on the left. Okay, so shifter, not to be confused with shift register, which we'll talk about later. Shifters are purely combinational, right? We tell how much we want to shift it by using the shift amount, and then, so say we want to shift by 3 bits to the left, then we select that input and feed that to our output Y. And so we can think about the same thing for a logical right shift, similar idea, an arithmetic right shift. So here I've drawn it out with the different bits, A3, A2, A1, A0. And so you can see, for example, that Y3 is, if we shift by 0 bits, this top input is the 0 input for our multiplexer. If our shift amount is 0, 0, we just get A3, A2, A1, and A0. We don't shift A at all. We send it to our output Y. But if we shift by 1 bit, now instead of A3, everything gets shifted shifted left by 1 bit. So we get A2, A1, A0, and then we get a 0 on bit 0 of Y. And so forth, right? So we've just shown it with the bits here delineated. And so when we shift by 3 bits, for example, now the only bit we have left, we shifted left by, A3 to A1, A0. All of these bits got shifted off to the left, and we have A0 followed by 3 zeros. And so we get A0 followed by 0, 0, 0. Logical shift right is very similar, but now what's getting, right, we have A3, A2, A1, A0. So as we shift right, bits are falling off to the right and we're getting zeros. So we'll see the only case where we don't get 0 on that top bit of Y is when there's no shift, right? When shift amount is 0. Otherwise, those zeros are shifting in onto the left. So here, in all those cases, either shift right by 1, 2, or 3 bits, we're going to get zeros in that most significant bit, and so forth, right? Only that bottom bit gets, first a 0, and then once it shifts right by 1, we get A1, and then by 2, A2, and by 3, we get A3. So the difference between arithmetic and logical shift is instead of shifting in zeros onto the left, we're going to shift in the most significant bit. So instead of shifting in these zeros, those are tied to A sub 3, the most significant bit of the input, A bit 3. And same thing for these ones. And same thing for all of these options here. So we can use shifters as multipliers and dividers. So just like in decimal, if we shift a value left, let's say we have some number 53, and we shift it left by 2 digits, we're going to get 53, 0, 0. And that's the same as multiplying 53 times the base, 10, to the number of digits that we shifted it. So in this case, 53 times 100. Yep, that's what it gives us. And so it's the same in binary. If we shift a number left by n bits, binary digits, that's the same as multiplying the number by 2, the base, to the nth power. So let's take an example. Let's suppose we have some number 3 or something, and we shift it left by 2 bits. Shift it left by 2 bits. So these 2 bits are going to fall off, and zeros are going to come in from the right. And so we get 0, 0, 0, 0, 1, 1, 0, 0. So we expect this to be, well, our original number was 3, shifted left by 2, should be 3 times 2 to the 2. Right, this is the number of bits we shifted. So 3 times 4 should be 12. Check. That's what we got. And here's another example. Suppose we have the value 1. We shift it left by 3 bits. We expect the result to be the original number, A1, times 2 to the number of bits that we shifted it, 3. And in fact, that's true, right? We shift that 1 left by 3 bits, those fall off. We put zeros in the front, and we get 8. And this works for positive and negative numbers. So let's suppose we started with -3, and we shift it left by 2. We expect that to be -3 times 2 to the 2, -3 times 4. We get -12. Shift this left by 2. Those fall off. We put zeros on the right. We get 1, 0, 1, 0, 0. And in fact, this is -12. We could take the 2's complement to make sure the magnitude is 12. We know it's negative. And so invert the bits, add 1. Yep, the magnitude is 12 and it was negative. So in fact, we get our -12. Right shift is the opposite, right? When we right shift and specifically use arithmetic right shift, that's a symbol for arithmetic right shift, by n bits, it's the same as dividing by 2 to the n. And we can do our decimal analogy. Again, let's say we had some number 37,000 or something, and we shift it right by 3 digits. that would be the same. So let's see, we shift it right by 3 digits. Those 3 fall off, and we get, 37,000 becomes 37. That's the same as the original number, 37,000, divided by the base 10 to the number of digits we shifted right. So divided by 10 to the 3. So 37,000 divided by 1,000. Yep, that's 37. So same principle here. Let's suppose we start with some number, in this case 8. We shift it right by, we arithmetic right shift it by 1. In this case, it, arithmetic or logical shift would have been the same, but it's important for sign numbers. So arithmetic right shift by 1 bit, we expect it to divide 8 by 2 to the 1. And in fact, we shift this right by 1 bit. Arithmetic right shift this by 1 bit. We take this sign bit, and that's what gets shifted in. And we get 0, 0, 1, 0, 0. In fact, we get 4. So 8 divided by the number of bits, divided by 2 to the number of bits that we shifted, arithmetic right shifted. We get 8 divided by 2 is in fact 4. And this can work for our negative numbers too. So here we have minus 16. We want to arithmetic right shift it by 2 bits. So these 2 fall off. And remember, we shift in the most significant bit, or the sign bit. So we shift in 2 1s up here, and we get 1 1 1 0 0. And in fact, that is minus 4. So we get minus 16. We arithmetic right shift by 2. It's the same as dividing it by 2 to the whatever number of bits we've right shifted by, 2 to the 2. So the minus 16 divided by 2 to the 2. Yep, we get minus 4. Check. And so shifters are, it turns out, a lot cheaper than kind of general purpose multipliers. So if we can ever get away with doing multiplication or division as a shifter instead of using a multiplier divider, it's going to be a lot cheaper, less hardware, lower power, etc. So it's a simple way of doing multiplication and division by powers of 2. So let's talk about multipliers and dividers and see how to build them. So multipliers, we've done multiplication longhand in decimal before, and it's similar process in binary, but actually a little bit simpler. We're going to perform our multiplication by creating these partial products and then adding them together. So, right, we 2 times this entire multiplicand. So 2 times 0, 0, 2 times 3, 6, 2 times 2, 4. And then we're going to shift over because, right, we want to be actually in one place over, because this 4 is in the tens place, not the ones place. And we do 4 times 0. We write 4 times this entire multiplicand again. 4 times 0, 0. 4 times 3, 12, carry the 1. 4 times 2, 8, plus 1, 9. And then we add them together. Right, we add those partial products together, and we get the result. Okay, so in binary, it's going to be the same, except a little bit easier in that, while multiplying the multiplier by the multiplicand, well, these bits down here, I'm still going to multiply that 1 times that entire multiplicand, or if there's a 0, this most significant bit is a 0, it's going to just be all zeros. So it's either, my partial product will either be the multiplicand, if the multiplier bit is 1, or all zeros if the multiplier bit is 0. And so these partial products we can see are the multiplicand, the multiplicand, the multiplicand, and then finally zeros. So it's easier in that way, in that the multiplication is easy. It's basically an AND gate of the multiplicand with the multiplier bit. If that bit is 0, we want it to be 0, but if it's 1, we want it to be whatever the multiplicand is. And then we add those partial products together and get the result. In this case, we have 5 times 7, and we get 35, which is in fact what we get, 32 plus 3. So how do we build this? Well, right, we build it by looking at how we perform those or calculate those partial products. So here's a 4x4 multiplier. We have 4-bit operands, and we could get up to 8 bits as the product, as the result. And so when we do, unlike addition, if we have 4-bit operands, we get 4-bit result. With the multiplier, 4-bit operand gives us 8-bit results. 16-bit operands, we get 32-bit result. And so we can see, like I said before in words, these partial products are going to be the multiplier ANDed with each bit of the multiplicand. So B0 and A0, B0 and A1, B0 and A2, B0 and A3. And now we should move over a spot, and then we get B1 and all of those bits. B1 and A0, B1 and A1, B1 and A2, B1 and A3. And same thing, B2 and all of those multiplicand bits. And finally B3 and all of those multiplicand bits. And then we add them together to get the final product. Okay, and so we can see here on our circuit, we have these adders here to start with, and the carry-ins have 0, and we perform A0, and well, we start with B0, ANDed with all of the multiplicand, the A bits, B0 and A0, B0 and A1. And then we add that to B1. Right, this one we just goes directly down to product bit 0, and then we're going to add these two together. And that's performed here. And then we're going to add these 3 together. Right, 1, 2, added to the third one. And so forth. And so what we notice about this is this circuit, well, it's a 4x4 multiplier. It's quite a bit of logic, a bunch of adders, and some AND gates to perform that multiplication. So multiplication is actually pretty expensive. And some very simple processors, microprocessors, don't have that multiplier or divider because of the expense of the hardware. And so instead of having that hardware, that multiplication or that division will be done in software. So let's talk about dividers. Here's an example of one that we've done, decimal division. 2584 divided by 15 ends up being 172, remainder 4. So we have our operands that we're going to operate on, A divided by B, and we're going to get our quotient plus our remainder divided by B. And so here's the longhand, which we've all done before. 15 goes into 25. Well, if it's in there once, subtract 15, and we get that. What's left is 10. Bring down the next digit, and we have 108. How many times does 15 fit in there? Fits 7 times. 7 times 15 is 105. So subtract 105. We get a 3. Bring down our last digit, 34. How many times does 15 fit into that? 2. 2 times 15 is 30. We subtract that, and we get 4, and that's our remainder. So we get 172, remainder of 4. And so I'm going to show a slightly different way of doing this because this is how we're going to do it in hardware when we do binary division. And so we could think of this, we're trying to see which of these numbers, you're shifting it in basically from the right, we're doing a left shift and seeing which, at what point does that number fit into, or does 15 fit into it? And so we start with 2, we try to see, well, does 15 go into 2? No, in our heads we skip that part because we obviously know 15 doesn't go into 2, but we didn't go to 258, right? We stopped when we got to 25 because we said, oh yeah, 15 does fit into 25. So, but generally we'll start with that most significant digit and say, okay, does that fit? Nope, 2 minus 15 is negative, it doesn't fit in there. So shift it again, shift that that number to the left again, and so we get 25 now, and we say, does that fit? 25 minus 15, yep, it fit. And so we can see that that it fit, and it fit once into there. And so now we say, okay, well, great. This is what we had left over. 25 minus 15 is the 10. So now instead of using this 25, we say we're going to use whatever is left here as the amount that we're going to now shift over and bring down the next digit. We're going to say, well, how many times does 15 fit into that? It fits in 7 times. And now we see 3. Again, instead of the 105, because this is positive and not negative, it did fit. We're going to bring that 3, and that's what we shift over and bring in our last digit, 4. Okay, so another way to think about it, because that's what we're going to do in our binary division. So we're going to perform division, binary division in a similar way. So this is unsigned binary division. So we have our A here is 13 divided by 2. We expect to get 6, remainder 1. Right? 6 times 2 is 12, and then we have a remainder of 1. Okay, so let's take a look at that. So we have our A here, A3, A2, A1, A0. And the first thing we're doing is going to take that most significant bit of A and bring it in, shift it in from the right. So we have A3, and we're going to see if our B, our divider, fits into that. So we perform 1 minus 2, and it doesn't, right? It's negative. So we say, okay, well, this was a negative result. That means that 2 didn't fit into that. And so that means we put a 0 into that quotient bit. Okay, so that's fine. So we take A3, this value, this entire thing, we shift it left by 1 bit. So A3 is still here now. And we take our next bit, A sub 2, and shift it in from the right. And now we check again. We say, hey, does our divider fit into that? So 3 minus 2, yes, it does. So it's positive. Now the result is positive. 3 minus 2 is 1. And so because it's positive, we put a 1 in our quotient bit there and say, yep, that fit. It fit. That's one nice thing about binary. It's either going to fit or not. It's not going to be a multiple of it. Right? So it's going to either be a 1, it fits, or it's negative result, or it's a 0, it doesn't fit. Okay, so that fit. 3 minus 2 is 1. And we take this value, our 1, and that remainder is what we're going to shift now left, and then bring down the next most significant bit, our A sub 1, into that least significant bit. Okay, and now we say, okay, let's see, does 2 fit into 2? Yep, 2 minus 2 is positive. Got a positive result. 2 minus 2 is 0, right? 0 is considered a positive, so 2 minus 2 is 0, and so that's positive, it's not negative. And so we get a 1 in the next most significant bit of the quotient. And then we take that result, well, it's all 0, so almost like you can't see it, but shift that left by 1 bit, and finally bring in our last bit of our of A. So A sub 0. So that's A sub 0. And we check and we say, oh, okay, does 2 fit into that? 1 minus 2 is -1. Oh, it's negative. So that last bit is 0, and this is our remainder. It didn't fit it. It didn't fit. And so our quotient is 6. And this is actually, that last bit was that last step of the division process, and our remainder is 1. And so we can write this in algorithm form. So we have this this r prime, this remainder value, and we want to perform a divided by b equals q plus r over b, where r is that remainder. And so we're going to do this for I equals n minus 1 to 0. For starting at this most significant bit of the dividend, the thing we're dividing of a. And we're going to say, okay, we're going to initialize this remainder to 0. So we have, let's do our 4-bit example. So we start with it as 0, 0, 0, 0. And then we shift this left by 1 bit. So that bit falls off. And we shift in a sub I, where a is that in the first iteration is the most significant bit of a. So now we have 0, 0, 0, a sub 3. That most significant bit, and that's this step right here. And now we're going to perform this this difference, r minus b. We're going to check if b fits in there. So this is r minus b. And we're going to say, well, if that difference is less than 0, so if it's negative, then it didn't fit. And we're going to keep that remainder. And we're going to say, hey, it didn't fit. So that quotient bit is 0. Okay, so that's our first step, our first iteration. And so we didn't do the else step in this case. We'll see what happens on the next step. And it's now going to repeat because we're in this for loop for I equals n minus 1 to 0. And so now we're in the second iteration of this. So now n is equal to n minus 2. We have r prime. So r prime, in this case, was 0, 0, 0, a sub 3, which was 1. So we'll just leave it like that. And now we're going to shift this r prime left by 1 bit. So now we're going to get 0, 0, a sub 3, right? This 0 falls off. And we shift in the next most significant bit, a sub 2. And that's what's happening here. And now we're going to say, okay, we're going to perform that difference again and say r minus b, does that fit? Does b fit into that value? In fact, it does this time. And it says it's d less than 0. No, that's not the case. In this case, it's greater than or equal to 0. It's 1. And so now we make our quotient sub I. So q sub 2 in this case is equal to 1. And now we, instead of passing this forward, we pass the difference forward, which is our 0, 0, 0, 1 into our r prime or remainder prime. Okay, and now we say, okay, remainder prime equals d, which is 0, 0, 0, 1. That gets shifted left by 1 bit. So 0, 0, 0, 1 gets shifted left. Drop that bit, and the next most significant bit comes in. In this case, a sub 1, which in our case was a 0. So now we're at this step. And now we check and say, does b fit into that? We perform that difference again, r minus b. Yes, it does. Is d less than 0? Nope, it's not less than 0. So we're in the else case. And we say, okay, well, q is 1. It's this one. And we make our r prime equal to that difference. Okay, and now we go to our last iteration. R prime was 0, 0, 0, 0, that difference. and we shift it left by 1, lose that bit, and we shift in the last bit of A, which is A sub 0. In this case, it's a 1, and we get 0, 0, 0, 1. Again, we're now at this stage, 0, 0, 0, 1. We perform that difference. 1 minus 2, is it less than 0? Yes, it is. Our last quotient bit is 0. Q sub 0 is 0, and then R prime is equal to R. It's just equal to that. And so now we're at the end of the iterations. We've gone from I equals n minus 1 to 0, and now we're done with that for loop, and we say R equals R prime. So remainder equals this R prime value. And we get our result, which is 6, 0, 1, 1, 0. It's this value here. This is our quotient, and our remainder is 1. Okay, so how do we build this? Here's how we build it. We have a box here. Each of these boxes is shown here because of space. We didn't write all of the names on those little boxes in this big figure. But inside this box is this circuit. And this circuit is basically performing, this adder is performing subtraction. As you can see that we're feeding in the inverse of B plus 1 into the carry in. So that's doing whatever this is, right? 0, 0, 0, A sub 3. This is that first iteration, 0, 0, 0, A sub I, and this in the first iteration is A sub 3. So each of these is performing an iteration. This is the n minus first iteration. This is the n minus 2 iteration. This is the n minus 3 iteration. And this is the n minus 4 iteration. So in this case, n is 4, and so we have the bit 3, bit 2, bit 1, and bit 0 of A being shifted in. Okay, so this is performing that difference of R, right? This is 0, 0, 0, A sub 3 to start with, R minus B, because we have the inverse of B coming in and 1 on the carry in. So this is performing subtraction, and then we get our difference out of it. We want to know, well, we're either going to feed that difference forward as R prime. That's in the else case. Or we're going to feed on just this remainder if the result was negative, if B didn't fit. Okay, and the carry out, this is just a ripple carry adder. So feeding into these other boxes. And the key here is that we want to look at what is the result of that difference. And so what we want to look at is this most significant bit of the difference, D sub 3. This is that most significant bit of the difference, and that will determine what we choose, right? If it's negative, then Q sub I, in this case Q sub 3, right? If this is negative, this is a 1, so Q sub 3 is the inverse of that. It'd be 0. And if it's negative, R prime is equal to R. So if it's negative here, we want to feed R into R prime. It didn't fit. And so this is an output. This is the difference of the most significant bit. So it tells us whether the result was negative. And then we feed that into these are inputs into each of those n inputs that select the multiplexer. Okay, so each of these is performing one iteration. Each of these kind of rows is performing one iteration of the algorithm. And then you can see we take so whatever R prime is, we take it, shift it left by 1 bit, and then shift in the next most significant bit of A. Same thing, next row, take that R prime, and then shift in the next most significant bit. And for the final row. Okay, so as you can see, this divider also quite expensive, just like the multiplier, adders, multiplexers. It's going to cost us quite a bit to build just this 4x4 divider.